Picture a single moment at a busy supermarket checkout. A cashier scans a barcode, the register beeps, and the price drops onto the receipt. Behind that beep is an online transaction processing system, or OLTP. Its entire job is to execute a high-speed lookup, find the price of that specific box of cereal, and record the sale in a matter of milliseconds. Multiply that by thousands of registers across hundreds of stores. The system processes a relentless stream of tiny, independent inputs. It is the operational heartbeat keeping the business alive, moment by moment. But then, a corporate executive asks a different kind of question. They don't want to know the price of one box of cereal. They want to know the total revenue for every store in January compared against the inventory from last week's promotion. If you try to run that massive historical query on the live checkout database, the machinery jams. Scanning millions of rows requires immense processing power, which starves the system of resources and literally locks up the registers in the stores. Customers are left waiting. A database engineered to find a single item with split-second precision cannot simultaneously scan years of history without collapsing. The physical architecture reaches its limit. To answer those massive historical questions, the data has to be physically extracted from the live operational environment. This is the data warehouse, an entirely separate, vast physical infrastructure built exclusively for deep analysis. The bridge between the checkout aisle and this archive is a continuous, automated process called ETL, extract, transform, and load. It pulls raw, scattered data points from the daily operations, cleans them into a standardized format, and deposits them into this massive repository. Isolating the operational pulse from the analytical archive allows a company to study its past without destroying its present. Once you dump petabytes of historical records into this warehouse, a new problem emerges. How does an analyst actually find anything inside that mountain of data? This map shows how engineers organize the chaos, a framework called the STAR schema. At the absolute center sits the fact table. Think of this as the massive sun of our solar system. It holds the raw, unchangeable logs of every single transaction event, growing larger with every passing second. Orbiting that sun are the dimension tables. These smaller planets contain the descriptive context for all those isolated facts, the specific details of the who, what, where, and when. Instead of blindly scanning billions of raw facts, an analyst uses these dimensional orbits to filter the search. You select the time and location dimensions, and the system instantly illuminates only the relevant slice of transactions. This design turns a sprawling, disorganized dumping ground into a navigable, relational universe. As a business scales, the questions get harder. Analysts don't just want to sort by product. They want to drill down into brand, package size, and fat content. As we see in our diagram, the architecture adapts by breaking those dimensions down further. Smaller subcategories begin orbiting the main dimension planets. This branching pattern is known as the snowflake schema. Even with these complex, nested layers of context, the core design remains intact, a heavy center of unchangeable facts, wrapped in layers of descriptive detail. But scanning billions of rows takes processing power. If executives request the exact same complex revenue report every morning, the servers waste enormous energy crunching the same math from scratch over and over. It's like a chef chopping the same ingredients for every single order instead of doing the prep work before the dinner rush begins. This diagram shows the database equivalent of meal prep, the materialized view. Thousands of records funnel through a mathematical filter, and the single resulting number is saved into its own distinct table. The system runs the heavy calculations once, aggregates the totals, and saves the final numbers onto a dedicated cheat sheet. When the morning report is requested, the system just hands over the completed answer. The heavy lifting is shifted away from the chaotic moment the question is asked, back to the quiet moment when the data is first written. Take that concept of pre-calculating answers and push it to its absolute limit, and you get a data cube. This visualization shows how a data cube works. Millions of disparate data points snap together, allowing an analyst to instantly slice and dice pre-calculated metrics by region, by date, by product, and see the results in real time. At the cash register, a single database writes localized events as fast as possible just to survive the day. But in the warehouse, a completely different architecture organizes that history to reveal broader patterns. By physically separating the data, then logically restructuring it, businesses extract actual intelligence